we have attractive Coulombian forces. For that, Q1, Q2 must be less than 0. Now, attractive Coulombian force means the force must be attractive in nature. Now, when this force will be attractive in nature? When we... So, that is why the Coulomb's law is valid only in case of the force will be reduced by that much. That is, more the relative permittivity, lesser will be the force. That means these two charges will be interacting with the very lesser, having only a magnitude part. So the important concept always what you will find whenever the same two charges are placed in a medium, or whether force experienced by a charge placed near a source charge. Now there is one key point. What is that? The electric field is the characteristic knowledge test. Let's see what the knowledge tests have. So here are some questions that are related to this topic that can be asked in board exams. If you have understood it, the concept check. Now let us see. The general question that can be asked in the exam is general question, the repulsive Coulombian force. That is, it is for Q1 is Q2 is always greater than 0. How we can represent this repulsive Coulombian force? If we have the two like charges, that is two negative charges. This one is the negative charge and this one is also a negative charge. So this is the direction where the repulsive forces will be present. So similarly, we have another like charges, that is two positive charges. So repulsive Coulombian forces will always point opposite to each other. This is how, and Q1, Q2, the product of Q1, Q2 will always be greater than 0. Here see, if we have two minus negative charges, here see, if we have two negative charges, this negative charges, and here this negative charges, negative into negative will become again positive, that is it will be greater than 0. And if we have two positive charges, two positive product of positive charges will become greater than 0. So if this situation is asked, what is the significance of Q1, Q2 is greater than 0? That means we are having the system of two like charges. This is the one concept. Next we have attractive Coulombian forces. For that, Q1, Q2 must be less than 0. Now attractive Coulombian force means the force must be attractive in nature. Now when this force will be attractive in nature? When we have the two unlike charges. That is, if one is negative charge and the other one is positive charge. So here what we are finding, the Coulombian force is pointing towards each other, that is, this is attractive in nature. So whenever it is asked if Q1, Q2 is less than 0, that means it signifies that one of the charge we are dealing is negative and the other charge has to be the positive. Then only this product will give us the attractive Coulombian force. So this is an important concept check related to the Coulomb's law. When the Coulomb's force are repulsive, so with which type of the charges we are dealing, and when the Coulombian force is attractive, with which type of the charges we are dealing. So please keep this in mind. Next is limitations of Coulomb's law. So all the important derivations related to Coulomb's law we have learned. Now there is one limitations. You might be reasoning that it is valid in all situations, but it is not at all. It is valid only under the following condition. Let us see. Whenever the electric charges must be at rest. So this is again a keyword. When the charges are at, then only the Coulomb force exists between these two charges. When the same charges are in motion, then this force, this law is not at all valid. Next is the electric charge must be the point charges. Again here the term point charges is coming, whose meaning is that the dimension of charges must be much smaller than the separation between them. So that is why the Coulomb's law is valid only in case of the point charges. Next we have the separation between the charges must be greater than the nuclear size. That means within the dimensions of nuclear size, this Coulomb's law has no application, because there the nuclear forces dominates over the Coulombian forces. So these are the three cases, conditions under which the Coulomb's law is valid. Now next is dielectric constant or relative permittivity, another very important topic. Now see, first of all, what is permittivity? So permittivity is the property of a medium which determines the electric force between two charges situated in that medium. In the previous article, we have learnt that whenever two charges are placed, there is a force between them. But now here, we will be concerning about the medium in which these two charges are being placed. So what is the role of the medium? With the help of an example, we can find that the force between two charges located some distance apart in water is about 1/80th of the force between them when they are separated by the same distance in air. What does this statement mean is that, suppose if we are having the two charges Q1 and Q2, that are present in air separated by a certain distance. So naturally a magnitude F, force of F will be present in between these two charges. But when the same two charges are present in a medium, let us suppose the medium becomes water, the magnitude of charges are same, the separation between them is again be the same, everything is same, only the thing is that we have changed the medium, which is water. So now whatever the force is acting between them in water will be 1/80th time that the force which was present earlier between them when they were in air. That means the force is reduced. That means whenever the charges are placed in a medium, the force will be reduced. Now here what I am referring is certain table, a relative permittivity of certain mediums. The first medium is vacuum, whose value is 1. Air we have 1.00054 and in water we have 80. So see here, the medium which is having that much greater electric constant, that much force will be reduced by that much. That is more the relative permittivity, lesser will be the force. That means these two charges will be interacting with the very lesser magnitude in a medium, whereas in air they are interacting with the greatest magnitude. That is what is the concept of relative permittivity is all about. So why the force in the medium is reduced? The force in a medium is reduced because the absolute permittivity of water is about 80 times greater than the absolute permittivity of free space. Here you can find is that the permittivity of water is 80 times that in the vacuum. So more is the relative permittivity, the lesser will be the force present between them. Lesser is the permittivity, more or the strong force will be present between the two charges. This is the concept of the permittivity. So directly, in indirect sense, it gives us the magnitude of the force, how the force is going to be affected when the charges are present in different media. Now let us find one formula related to this. Whenever the force is present between the two charges in vacuum, we are having a formula F vacuum is equals to 1 upon 4 pi epsilon naught. Here we are dealing with pi epsilon naught and Q1 Q2 by R square. But when the same charges are present in any medium, what the formula will be? F medium. See here, we have to write F medium, which becomes 1 upon 4 pi epsilon. Here the difference is that we are not writing epsilon naught because epsilon naught is the permittivity of a free space or a vacuum, whereas epsilon is called as the permittivity of the intervening medium. It is called as the permittivity. Yani ki this epsilon is the deciding factor which will decide what will be the magnitude of the force between the same two charges which were there in a vacuum. So what is the effect of this medium? If we will divide these two forces, that is force in vacuum and force in medium, the ratio of these two forces, we will get the ratio of epsilon upon epsilon naught, and this ratio is called as the relative permittivity, which is equals to epsilon upon epsilon naught. So this is also equals to ratio of F vacuum to the F medium. So the definition of relative permittivity, it is the ratio of force between two charges placed some distance apart in free space, ratio of force in free space to the force between the same 2 point charges when they are placed same distance apart in a given medium. So it is the ratio of two forces. So another important concept related to this relative permittivity is that it is a dimensionless and a unitless quantity. Keep in mind, for epsilon naught we have defined the unit in the previous article. In this video only I have given you the unit and the value of epsilon naught, but here for the relative permittivity it is unitless and a dimensionless quantity. It will be having only a magnitude part. So the important concept always what you will find whenever the same two charges are placed in a medium or whether they are placed in a vacuum, the force present between them in a medium will always be less than the force between the same two charges when they are present in the vacuum. That means in vacuum the charges experience the greatest amount of force, and in any other medium the magnitude of the force always. Have you ever wondered how other electric charges will interact if they pass nearby an object with a known amount of net charge? That means if in a space huge amount of charge is present on a body, what will be its effect on other smaller bodies which are placed near to it? In order to understand this statement clearly or in detail, you must know the concept of the electric field. Now, in order to understand the concept, let us imagine a situation where we are having a charged body plus Q in the space called as the source charge, and another test charge having a small charge on it called as the test charge body, denoted by the Q naught. It is initially free to move in a space because it is not under the influence of this plus Q source charge. Now, whenever we place a source charge in a space, the region around it gets modified because of its present, and this modification we have shown by the electric field lines, that they are the imaginary field lines. Whenever the test charge will come under near this source charge, it will experience a kind of a force that is because of the presence of the electric field. Here lies the concept of the electric field. Now, so let us understand the another situation where we are having the same source charge which is present in the space. Here we have the same source charge, but this time a test charge is placed near to the source charge. So now it will experience a kind of a force. Now, from where does this force come? This is because of the presence of the electric field around the source charge. This electric field will exert a kind of a force on the test charge, and this is all about the concept of electric field. That means it helps us to find out the magnitude of the force experienced by the other smaller bodies. Now, next we have the concept of the electric field. Now, let us begin with our important topic, that is its definition and what are the important steps in its derivation. So, what we are having first, definition. How we can define it? It is defined as the electrostatic force per unit test charge acting on a vanishingly small positive test charge. As I have shown you, if we are having a source charge plus Q placed in a space, the region around it gets modified by the presence of the electric field. Now, if a test charge is placed near to the source charge, it will experience a kind of a force. Now, mind it here, the test charge have to be the vanishingly small. Why is it so? That is how we can represent it. We can represent it as a limiting case of Q naught is tending to 0. This is the very important part in defining the electric field. So, what will be the definition? It is defined as the limiting case where Q naught is tending to 0 force per unit test charge. Now, I will explain why we should need a vanishingly small positive test charge. But before that, let's go for the electric field. Here, E is a vector quantity. Why? Because its direction is same as that of the force F experienced on a positive test charge. If we are having a test charge is placed, just a minute, let me erase. So now, if we are having a test charge placed in this at this point, so it will experience a force in this direction. If we place the test charge at this point, it will experience a force in this direction. Or if we place a test charge in this direction, it will experience a force. So whatever, depending on the position of the point charge, the direction of force keeps on changing, and hence the direction of electric field keeps on changing. That is why we call it as a vector quantity. That means its direction is same as that of the force experienced by the test charge. Now, there is one concept check. What it has to say for us? That means the test charge Q naught, it may disturb the charge distribution of the source charge, and hence it may change the electric field which we want to measure. If we take this Q naught to be of measurable quantity, that means if it is of a certain big amount of quantity, 1 coulomb, 2 coulomb or certain microcoulombs, that means its presence can affect the presence of the field lines of the source charge which we do not want. That is why in the definition we have defined Q naught is tending to 0. We cannot take the value of Q naught exactly 0, but it is tending to 0, 0.000 something coulombs. Value should be 0.00 in millicoulombs. That means the test charge Q naught must be small enough. Why? So that it does not change the value of E. So if in definition, if you give this point, it will be wrong statement. In definition, you have to give only this much statement in limiting case. Next, we are having units and dimensions of electric field. What are the units? First of all, as it is, electric field is defined as the force experienced per unit test charge. That means the unit of force is Newton, and for charge we have Coulomb, so Newton per Coulomb, or it is also called as volt per meter. Now, for the dimensions of electric field, as electric field is the force per, electric field is force per charge. That means MLT minus 2. It is the dimensional formula of force, and Coulomb is the dimensional formula of test charge. So, on solving this, we will get MLT minus 3A minus 1 will be its dimensional formula. Next, let us try to understand the physical significance of the electric field. As I have shown, the electric field lines are shown by this cases if we are having a plus Q source charge. That means the force experienced by the test charge Q naught is different at different points. So E also varies from point to point. As I have explained, if Q naught, the position of Q naught keeps on changing, so the direction or the value magnitude of electric field also keeps on changing. That is the important factor. So what we can say that E is not a single vector but a set of infinite vectors. So many vector directions are associated with the electric field. So we can say it is a set of infinite vector, not a particular direction. In a particular situation, it is having particular direction, but in a lump sum quantity, we will say we can have all the possible directions. So electric field is an example of a vector field. Next, by knowing the electric field at a point, we can determine the force on a charge placed at that point. So in spite of not using the Coulomb's law, we can also find the force in terms of the electric field. So this is its physical significance. It helps us to find the force experienced by a charge placed near a source charge. Now there is one key point. What is that? The electric field is the characteristic of a system of charges. That means this electric field is the characteristic of the source charge, not of the test charge. So mind it here carefully. Electric field is the characteristic property associated with the source charge or a system of charges. It is independent of the test charge. A test charge has no significance in its formulation. That is the important key point. Next, we will go for the derivation, the steps that you will be writing in exams or whenever it is any question related to this concept is asked. If you will follow these steps, you are going to get the full marks. Let's see what are the steps. We are first finding the electric field due to a point charge. For that, let us imagine a situation where we have placed a point charge called as the source charge at the point O. Now at a point P, we want to find its effect, that is what will be the electric field intensity at the point P. So we have to place a test charge of vanishingly small magnitude at the point P. Now naturally this Q naught will experience a force in this direction. Why? Because they are of the similar nature. So it will experience a force in this direction. Now the separation between the Q and Q naught is R. Now, what will be the Coulomb's force experienced between this Q and Q naught? Already earlier we know already that it is 1 upon 4 pi epsilon naught Q naught by R square, and this is the unit vector R which is pointing from O to P. Now, according to the definition of the electric field, what is that? Electric field is equals to F upon Q naught. So, if you divide this equation by Q naught, so this Q naught and Q naught gets cancelled out. That is why in my previous article I have told you that electric field is independent of Q naught. It has nothing to do with Q naught. It is the characteristic property of Q only. So what magnitude wise or in formula we will get for the derivation is 1 upon 4 pi epsilon naught Q by R square and unit vector R, that is it is pointing in this direction. That is, it is just a characteristic of the source charge. It has nothing to do with the test charge. So what will be the final magnitude wise if you want to write? It is simply equals to K Q by R square. That means it varies inversely with the R square. Next, we will try to understand the certain key points. What are the key points? As we have seen that the electric field varies inversely as R square. That means at all points on the spherical surface drawn around the point charge, the magnitude of E is same. That means if we will have a spherical surface, if we will draw a spherical surface like this around a source charge, at all the points on this spherical surface, the magnitude of E is going to be the same. That is called as and it is independent of direction of R, and this is called as the spherically symmetric or a radial field. That is the most important point. Why the electric field is a radial field or a spherically symmetric? Because at all the points on the spherical surface drawn around the point charge, the magnitude of E is same. That is why it is called as the spherically symmetric. Now, what is the importance of the electric field? Now, by this time you might have understood that electric field is a measurable effect generated by any charged object. It is called as the measurable effect generated. Next, in order to understand the nature of action at a distance force, so nature of action of the force, whether the force will be repulsive or attractive, the concept of electric field helps us to determine that. Now, next we are having the electric field lines, how we can represent the electric field lines. In case of a positive source charge, the electric field lines always point away from it. Always keep this in mind, they will always point away from it, because the test charge that we have taken Q naught, it is positive in nature. So naturally a repulsive force will be acting on the test charge, so electric field lines will be pointing away from the source charge. But if we are having a source charge as negative and we are having a positive test charge, mind it, here we have taken a test charge as a positive, so there will be an attractive force acting on this test charge. So electric field lines will always be pointing towards the negative source charge. Keep this in mind. For a negative source charge, the electric field lines are towards it. Now we are having one knowledge test. Let's see what the knowledge tests have. So here are some questions that are related to this topic that can be asked in board exams. If you have understood it well and write all the steps that I have explained, you will get the full marks. So go for these questions and present your answer very well. All the necessary steps which are required to explain the answers of these questions I have. Now let's begin with the topic electric dipole in detail. To begin with, a dipole is the separation of opposite electrical charges. That is, an electric dipole occurs when positive and negative charges are separated from each other. And it is usually seen in molecules having a covalent bonds, for example, water molecules and HCl molecules. So here, as you can see, we are having a negative charge and a positive charge separated by a some finite distances. That will constitute an electric dipole. Next, we are having the dipole moment. A term which is associated with the electric dipole is a dipole moment. How we can define a dipole moment? That when the two charges are separated by a certain separation, that is 2a. So a physical quantity which is denoted by a symbol P, it is equals to Q into 2a, and it is always pointing from a negative to a positive charge. So about this physical quantity we will learn more about in this article. Let's start with an axial line. How we can represent an axial line? So it is the line joining the centers of the two charges. That means if we are having the plus Q and minus Q, the line which joins their centers will be called as an axial line, or any point which lies on this axial line will be called as an axial point. So here we will be finding the electric dipole. Next we are having an equatorial plane. What is an equatorial plane? If we are having the same charges plus Q and minus Q separated by certain distance, so a plane which lies perpendicular to the axial line at the center will be called as an equatorial plane, and any point which lies on this equatorial plane will be called as an equatorial point. And one important point is that this equatorial point will always be equidistant from either of the charges. This equatorial point will always be equidistant. So at equatorial point and an axial point, this dipole will be exerting an electric field, and our aim will be to compute them.